What if I told you everything we see, the stars, the galaxies, even you and me, makes up less than 5% of the universe, the rest, a ghostly, invisible mystery? Scientists call it dark energy and dark matter, and together they account for a staggering 95% of the cosmos. But here's the thing, we have no idea what they actually are. Imagine standing in a room where 95% of the space is filled with nothing you can touch, see, or even detect with our most advanced instruments. That's the universe we live in, a cosmic puzzle so baffling it keeps physicists awake at night. Think about the energy it takes to light up a single star. Now multiply that by billions of galaxies, each with billions of stars. And yet, all that visible energy is just a tiny fraction of what's actually out there. The rest is hiding in plain sight, warping the fabric of space, accelerating the expansion of the universe, bending light in ways that defy logic. Somewhere in that shadowy 95% lies the answer to why our universe behaves the way it does. But how do you solve a mystery when the clues are invisible? This is where things get wild. Dark matter, whatever it is, acts like an invisible scaffolding, holding galaxies together with its gravitational pull. Dark energy, on the other hand, is doing the opposite, pushing the universe apart faster and faster. These two forces are locked in an endless tug of war, shaping everything from the smallest galaxy to the fate of the cosmos itself. And yet, after decades of searching, we've barely scratched the surface. So today, we're diving into 30 mind-bending theories that could explain where the universe's missing energy went. From hidden dimensions to cosmic ghosts, from flaws in Einstein's equations to entire universes beyond our own. Strap in, this journey is about to get cosmic. Let's rewind to the early 1900s when Albert Einstein was wrestling with a problem. His equations describing gravity, the famous theory of general relativity, predicted a universe that should either expand or collapse. But at the time, everyone thought the cosmos was static, unchanging. So Einstein did something radical. He added a mathematical fix, a sort of cosmic counterbalance to gravity. He called it the cosmological constant. Think of it like an invisible force pushing outward, perfectly cancelling gravity's inward pull to keep the universe in equilibrium. But here's the twist: when Edwin Hubble discovered in the 1920s that the universe was actually expanding, Einstein ditched his own idea, calling it his greatest blunder. The cosmological constant seemed unnecessary, yet decades later, astronomers made an even more shocking discovery. Not only is the universe expanding, it's accelerating. Distant galaxies are racing away from us faster and faster, as if some unseen energy is stretching space itself. Suddenly, Einstein's blunder didn't look so foolish after all. Today, many scientists believe the cosmological constant might actually be dark energy in disguise. It's the simplest explanation, a uniform, unchanging force woven into the fabric of space, driving the universe apart. But simplicity doesn't mean certainty. The numbers don't quite add up. Quantum physics predicts a cosmological constant trillions of times stronger than what we observe. If it's really out there, why is it so faint? Some argue it's evidence we're missing something fundamental, while others wonder if Einstein's fudge factor was just a lucky guess. Either way, this century-old idea is now at the heart of one of cosmology's biggest mysteries. But what if dark energy isn't a fixed force at all? Enter quintessence, a mysterious, shifting field that could rewrite everything we think we know about cosmic expansion. Unlike Einstein's static cosmological constant, quintessence is alive, changing over time like an invisible tide, ebbing and flowing through the universe. Picture it like this: if the cosmological constant is a steady hand pushing galaxies apart at a constant speed, quintessence is more unpredictable, sometimes pressing harder, sometimes easing up, as if the cosmos itself has mood. This idea isn't just poetic, it could solve some glaring puzzles. For instance, why does the universe's expansion rate seem to vary across different epochs? Observations of ancient supernova and distant galaxy clusters suggest dark energy wasn't always this dominant. Billions of years ago, gravity had the upper hand, slowing the universe's expansion. Then, around 5 billion years ago, something flipped. Dark energy took over, and the expansion began accelerating. A static cosmological constant struggles to explain this shift, but quintessence. It thrives on change. Theorists imagine quintessence as a kind of cosmic fluid, its density and pressure waxing and waning across cosmic time. Some models even suggest it could interact with dark matter, creating a dynamic dance between the two. Imagine a seesaw. As dark matter's gravitational pull weakens with the universe's expansion, quintessence grows stronger, tipping the balance toward acceleration. But here's the catch: no one knows what quintessence is. Is it a new fundamental force, a relic from the Big Bang, or something even stranger, like a hidden dimension leaking into our own? The stakes are high. If quintessence is real, it wouldn't just explain the past, it could predict the universe's ultimate fate. Unlike the cosmological constant's bleak forecast of endless, lonely expansion, quintessence leaves room for surprises. Could it someday reverse course, pulling the cosmos back together in a big crunch? Or might it grow so powerful that it tears apart galaxies, stars, even atoms in a far future big rip? For now, the clues are maddeningly vague, but with next-generation telescopes like the Vera Rubin Observatory set to map the cosmos in unprecedented detail, we might finally catch this elusive force in action or rule it out forever. One thing's certain: whether it's Einstein's constant or this ever-changing phantom, the mystery of dark energy is far from solved, and that's what makes it so thrilling. Every observation, every theory is a step closer to uncovering the universe's best-kept secret. Now let's talk about something truly unsettling: phantom energy. If dark energy is the mysterious force pushing the universe apart, phantom energy is its nightmarish counterpart, a hypothetical version so potent it could shred reality itself. Picture this: instead of gently accelerating the cosmos's expansion, phantom energy grows stronger over time, stretching spacetime until galaxies, stars, planets, and even atoms are violently torn apart in a cataclysm cosmologists call the Big Rip. This idea hinges on a bizarre twist. Phantom energy would have negative kinetic energy, meaning it doesn't just nudge the universe outward, it actively destabilizes it. Think of it like a car accelerating faster and faster, not because you're pressing the gas pedal harder, but because the brakes have turned into boosters. The more space expands, the stronger phantom energy becomes, creating a runaway effect with no off switch. The math behind this is both fascinating and eerie. Most models of dark energy assume its density stays constant or fades slowly, but phantom energy, its density increases as the universe grows, like a fire that burns hotter the more you feed it. If real, it would mean the cosmos has an expiration date not billions of years from now, but potentially as soon as 22 billion years, a blink in cosmic terms. One moment you're sipping coffee on Earth, the next the planet itself is ripped to subatomic confetti. Critics argue phantom energy is more speculation than science. For one, negative kinetic energy defies our everyday intuition. No known particle or field behaves this way. Then there's the observational problem. Current data on cosmic expansion fits neatly with simpler models of dark energy. Phantom energy's fingerprints, like subtle tremors in the fabric of spacetime, remain undetected. Yet the idea persists because it forces us to confront the wildest possibilities hidden in Einstein's equations. Could spacetime itself have latent instabilities we've overlooked? Might there be exotic particles or undiscovered physics that unlock this apocalyptic scenario? Phantom energy doesn't just challenge our understanding of dark energy, it dares us to imagine an end to reality as we know it. And in a universe where 95% of everything is invisible, that's a dare worth taking seriously. What if dark matter doesn't exist at all? That's the radical question at the heart of modified Newtonian dynamics, or MOND, a theory that flips the script on one of cosmology's biggest assumptions. Instead of invoking invisible matter to explain the universe's missing mass, MOND suggests something far more provocative. Our understanding of gravity might be wrong. Take galaxy rotation curves, for instance. Stars at the edges of spiral galaxies orbit so fast that, according to Newton's laws, they should fling off into space like a carnival ride gone haywire. The mainstream fix, dark matter's gravitational glue, holds everything together, but MOND offers a different solution, a tweak to gravity's rules on cosmic scales. Imagine Newton's famous apple falling from the tree, but instead of accelerating at 9.8 meters per second squared in weak gravitational fields, it drops just a little slower. Multiply that subtle shift across an entire galaxy, and suddenly those hyperfast stars make sense without any dark matter required. The idea isn't just a thought experiment. MOND predictions eerily match real-world observations of over 150 galaxies, their rotation curves aligning neatly with the theory's adjusted math. Even more striking, it anticipated bizarre phenomena like the Tully-Fisher relation, a tight link between a galaxy's brightness and its rotation speed, long before dark matter models could explain it. For supporters, this isn't coincidence, it's evidence we've been chasing a phantom. But here's where things get messy. While MOND nails galaxy-scale behavior, it stumbles when faced with larger cosmic puzzles. The bullet cluster, for example, a cosmic collision where visible gas and unseen mass visibly separate, shows gravitational effects without corresponding matter, a smoking gun for dark matter that MOND struggles to reinterpret. Then there's the cosmic microwave background, whose temperature fluctuations fit a dark matter-rich universe like a glove. Critics argue MOND is a patchwork fix, bending gravity's rules just enough to solve one problem while ignoring others. Yet its defenders counter that dark matter searches, after decades and billions of dollars, have turned up empty-handed. No particles, no direct detections, just a growing list of hypothetical candidates like WIMP and axions that remain stubbornly elusive. Maybe, they say, it's time to stop inventing invisible stuff and start questioning the foundations instead. The debate rages on, fueled by each new telescope and supercomputer simulation. Some theorists now explore hybrid models, blending MOND-like tweaks with just a bit of dark matter, a cosmic compromise. Others dig deeper into quantum gravity or hidden dimensions, wondering if the truth lies beyond both camps. One thing's certain, whether MOND is a dead end or a revolution in the making, it forces science to confront an uncomfortable possibility. What if the real missing piece isn't out there in the void, but in our most fundamental laws? At the heart of modern physics lies an elegant idea that every particle we know has a hidden twin. This is supersymmetry, a theory so compelling it's been called the mathematical diamond of particle physics. It proposes a cosmic symmetry so perfect that every fermion, the building blocks of matter like quarks and electrons, has a boson partner and vice versa. These hypothetical superparticles could be the key to unlocking not one, but two of the universe's greatest mysteries, dark matter and dark energy. Picture a shadow world identical to our own but just out of reach. In this mirror universe, electrons would have selectron partners, quarks would pair with squarks, and photons might dance with photinos. The lightest of these superparticles, often dubbed the neutrino, wouldn't decay or interact with light, making it invisible, stable, and eerily similar to what we expect dark matter to be. If supersymmetry is real, we're literally swimming in a sea of these ghostly particles right now, their collective gravity shaping galaxies while remaining utterly undetectable. But supersymmetry's ambitions don't stop there. Some versions of the theory suggest these superparticles could also influence dark energy, acting as cosmic pressure valves that tweak the vacuum of space itself. Imagine spacetime as a stretched rubber sheet. Ordinary matter bends it downward with gravity, while dark energy pushes outward. Supersymmetry introduces a hidden layer of tension in that rubber, subtle adjustments that might explain why the universe's expansion is accelerating. It's a two-for-one deal. Solve dark matter with neutrinos, and dark energy becomes a side effect of their quantum interactions. So where's the proof? Enter the Large Hadron Collider, the most powerful particle smasher ever built. For years, physicists hoped it would spit out superparticles, confirming supersymmetry in a shower of exotic debris. Yet after countless collisions at energies high enough to recreate conditions a billionth of a second after the Big Bang, nothing. No squawks, no photinos, not even a whisper of a neutrino. This silence has left theorists divided. Some argue we've barely scratched the surface, that superparticles might be just out of reach, requiring even higher energies or more sensitive detectors. Others propose tweaked versions of supersymmetry where these particles are stealthier, blending into background noise. But a growing faction whispers the unthinkable. What if supersymmetry, for all its beauty, simply isn't how the universe works? The stakes couldn't be higher. If supersymmetry falls, decades of theoretical work, including string theory's dream of uniting all forces of nature, could crumble. Yet its elegance keeps physicists hooked. Maybe the LHC needs an upgrade. Maybe we're looking in the wrong place. Or maybe, just maybe, the universe's missing energy is hiding in plain sight, waiting for a theory even stranger than this one. After all, in a cosmos where 95% of everything is invisible, shouldn't the answers defy our expectations? What if the universe's missing energy isn't lost, just hiding in plain sight, curled up in dimensions we can't see? This is the tantalizing premise of extra-dimensional theories, where the fabric of reality stretches far beyond the 3 dimensions we experience daily. Picture space as an infinite sheet of paper. To us, it's flat length, width, height. But to a microscopic ant crawling across its surface, that paper might harbor hidden folds, tiny crevices invisible from a distance. Now imagine those folds aren't empty. They're vibrating with energy, warping gravity, and subtly altering how the cosmos behaves on scales we can measure. String theory, one of the most ambitious frameworks in physics, suggests these extra dimensions aren't just mathematical quirks. They're physical realities, twisted into intricate shapes called Calabi-Yau manifolds. These structures are so compact, 1 billion times smaller than an atom, that they're essentially undetectable to our instruments, yet their influence might be everywhere. Think of gravity as a force that doesn't just pull between objects in our 3-dimensional world, but leaks into these hidden dimensions, diluting its strength and making the universe's energy balance appear lopsided. It's like trying to fill a bathtub with a sieve. What we perceive as missing might just be slipping through cracks we didn't know existed. But extra dimensions aren't confined to the ultra-tiny. Some models, like the brane world scenario, propose a far wilder idea, that our entire universe is a 3-dimensional brane floating in a higher dimensional space, like a leaf drifting on a pond. Other branes, parallel universes, could be just millimeters away, yet entirely invisible because light and matter are trapped on their own branes. Gravity, though, might bridge the gap. If it bleeds into the bulk space between branes, it could explain why dark energy's effect seems so faint. It's not vanishing, it's spreading out across dimensions we can't access. Testing these ideas isn't just hard, it's borderline absurd. How do you probe a dimension smaller than a quark or detect a parallel universe that doesn't share our physics? Scientists have gotten creative. Some hunt for tiny deviations in gravity at microscopic scales, where extra dimensions might subtly alter Newton's famous inverse square law. Others scour particle colliders for anomalies, exotic particles that could be echoes of higher dimensional vibrations. Then there's the cosmic microwave background, the afterglow of the Big Bang, which might bear faint imprints of collisions between our brane and another. The challenges are staggering, but so are the stakes. If extra dimensions are real, they wouldn't just solve the dark energy puzzle, they'd rewrite our understanding of reality itself. Forget parallel universes, we'd be living in a multidimensional one where gravity, energy, and even time behave differently behind the scenes. And here's the kicker: the very fact that we haven't detected these dimensions yet might be the biggest clue of all. After all, if 95% of the universe is invisible, why should its dimensions be any different? So next time you stare at the night sky, remember, the answers to cosmology's biggest mysteries might not be in the distant galaxies, but in the spaces between space, where the universe's secrets are curled up, waiting to be unfurled. Empty space isn't really empty, not according to quantum physics at least. At the tiniest scales, the vacuum of space is a seething, bubbling foam of particles popping in and out of existence so fast we can't detect them directly. These fleeting fluctuations aren't just quirks of quantum mechanics, they carry real energy, a kind of background hum to the universe known as vacuum energy. And here's where things get mind-bending. If you add up all this invisible energy lurking in every cubic centimeter of space, the total should be enormous. We're talking about a number so big it defies common sense. It's enough energy to rip spacetime apart in an instant. So why hasn't the universe self-destructed? Because the real-world effects of vacuum energy are almost comically weaker than theory predicts. When physicists crunch the numbers, quantum field theory suggests vacuum energy should be around 120 orders of magnitude stronger than what we actually observe as dark energy. To put that in perspective, it's like calculating the weight of a feather and getting an answer heavier than the entire observable universe. This glaring mismatch is often called the worst theoretical prediction in physics, a problem so baffling that even legends like Richard Feynman called it the dumbest problem in all of physics. The heart of the issue lies in how quantum fields behave. Every particle, electrons, quarks, photons, is just a ripple in its own underlying field, like waves on an ocean. Even when those fields seem calm, they're never truly still. Their lowest energy state still vibrates with what's called zero-point energy. Add up all those fields, and the total vacuum energy should be mind-blowingly dense. But when astronomers measure dark energy's actual influence on cosmic expansion, it's whisper-thin, just enough to nudge galaxies apart, not enough to tear atoms to shreds. Some argue the solution lies in cancellation. Maybe different fields' energies somehow balance out, leaving only a tiny residual effect we perceive as dark energy. Others propose radical revisions to quantum theory itself, suggesting our math misses hidden symmetries or undiscovered physics that tames the chaos. Then there's the unsettling possibility that vacuum energy is dark energy, but we're missing a crucial piece that explains why it's trillions of times weaker than expected. This isn't just academic curiosity. If vacuum energy were even slightly stronger, galaxies could never have formed. Stars, planets, life, none of it would exist. The fact that we're here to ponder this at all suggests an eerie fine-tuning, as if the universe dialed this energy down to an impossibly precise value. Is that a fluke, a sign of deeper laws we don't yet grasp, or something even stranger? One thing's clear: until we reconcile this titanic gap between prediction and reality, the vacuum of space will remain one of the universe's most frustrating and thrilling mysteries. What if the three-dimensional universe we experience is just an illusion, a cosmic mirage projected from a two-dimensional surface at the edge of reality? This is the holographic principle, one of the most radical ideas in modern physics, and it might hold the key to the universe's missing energy. The theory starts with black holes, those gravitational monsters so dense that not even light can escape. In the 1970s, physicist Jacob Bekenstein made a startling discovery. A black hole's entropy, a measure of its hidden information, isn't proportional to its volume, as you'd expect, but to the area of its event horizon. It's as if all the data about what falls into the black hole isn't stored inside but plastered across its surface, like a cosmic sticky note. This bizarre connection between surface area and information led theorists to a wild extrapolation. What if everything in the universe works this way? Imagine reality as a giant movie screen. The images you see, trees, stars, galaxies, appear three-dimensional, but they're really just projections from data encoded on the screen's flat surface. In this view, the universe's true storage drive isn't the space around us. It's a distant, two-dimensional boundary where information is packed at unimaginable density. And here's where dark energy enters the picture. If energy and information are fundamentally linked, as Einstein's E equals mc squared suggests, then the universe's missing energy might not be missing at all. It could be written on this hidden surface, manifesting in our 3D world as the mysterious force accelerating cosmic expansion. The math behind this idea is anchored in something called the AD/CFT correspondence, a theoretical bridge between two seemingly unrelated realms, a warped, higher-dimensional space anti-de Sitter space, or AD-S, and a lower-dimensional quantum field theory, conformal field theory, or CFT, on its boundary. In simpler terms, it's like saying a video game's entire 3D world could be perfectly described by the code written on its flat DVD. Apply this to the cosmos, and suddenly, dark energy's elusive nature makes a strange kind of sense. It's not a substance or a particle, but a shadow cast by the universe's underlying code. Critics argue the holographic principle is more metaphor than mechanism, a mathematical curiosity without experimental proof. But supporters point to tantalizing clues, like the way black hole physics and quantum information theory keep converging on this idea. If they're right, the implications are staggering. The holographic universe wouldn't just explain dark energy. It would mean reality as we know it is a kind of illusion, a 3D rendering of data we can't yet read. And somewhere, written on the cosmic boundary in bits we don't yet understand, lies the answer to why the universe is flying apart faster than it should. The question isn't just where the missing energy went, it's whether we're even asking the question in the right dimensions. Could the speed of light, that cosmic speed limit etched into physics textbooks, have been different in the distant past? This wild idea, known as variable speed of light or VSL theory, suggests that light didn't always zip through space at 299,792,458 meters per second. Instead, it might have raced faster in the universe's infancy, subtly rewriting the rules of energy and gravity when the cosmos was just getting started. The implications are staggering. If light traveled quicker in the early universe, it would have carried energy differently, potentially solving mysteries like the horizon problem. Why distant regions of space appear so uniform in temperature despite never having had time to communicate across vast distances. It could also tweak our understanding of dark energy, since the expansion rate of the universe is deeply tied to the speed of light. Imagine a cosmic reset where the fundamental constants weren't so constant after all, adjusting just enough to throw off our modern calculations of missing energy. But how do you prove something like this? Supporters point to flickers of evidence in the light of quasars, those brilliant galactic cores billions of light years away. Some studies claim to detect tiny variations in the fine structure, constant a number that depends on the speed of light when analyzing quasar spectra. If true, it would mean the laws of physics weren't set in stone but evolved over cosmic time. Critics fire back that these observations could be illusions, distortions caused by interstellar gas or measurement errors. After all, the speed of light is the backbone of relativity, and tampering with it risks unraveling everything from GPS satellites to nuclear physics. Yet the idea persists because it offers a tantalizing loophole. maybe dark energy isn't some exotic force, but an echo of a time when reality itself played by different rules. Whether a revolutionary insight or a fringe hypothesis, VSL theory forces us to ask a humbling question. Are the constants of nature truly constant, or are they just waiting for us to catch up to their secrets? Imagine a cosmic fluid so strange that it morphs from behaving like invisible matter to acting like repulsive energy, all while shaping the fate of the universe. This is Chaplygin gas, a theoretical substance that could solve two mysteries with one elegant twist. Named after a Russian physicist from the early 1900s who studied airplane wing aerodynamics, this exotic fluid starts its cosmic journey acting just like dark matter, clumping together under gravity to sculpt galaxies. But as the universe expands, it undergoes a bizarre transformation, thinning out and taking on the properties of dark energy, pushing galaxies apart. One substance, two roles, a cosmic shape-shifter hiding in plain sight. The math behind Chaplygin gas is deceptively simple. Picture a fluid whose pressure decreases as its density drops, the opposite of everyday materials like water or air. This counterintuitive behavior means that in the early universe, when space was denser, Chaplygin gas would have exerted minimal pressure, allowing it to clump like cold, dark matter. But as expansion diluted its density, its pressure would ramp up, resisting gravity and accelerating the cosmos, exactly what we observe dark energy doing today. It's as if the universe's missing ingredients were never separate entities at all, but different phases of a single, unified dark fluid. For a time, Chaplygin gas seemed like the perfect cosmic compromise. It neatly sidestepped the awkwardness of having two unrelated dark components dominating the universe. Observations of distant supernova and galaxy clustering even showed tentative support, with the gas's predicted expansion history loosely matching the data. But the cosmos rarely makes things that easy. Recent precision measurements of the cosmic microwave background, the faint glow of the Big Bang, have thrown cold water on the idea. The patterns in this ancient light reveal how matter clumped in the early universe, and Chaplygin gas's predictions are now in tension with what we see. It appears too stiff to explain both the smoothness of the early cosmos and the lumpy distribution of galaxies we observe today. Yet the story isn't over. Some theorists propose modified versions like a generalized Chaplygin gas, which tweak the equation of state to better fit observations. Others explore hybrid models where Chaplygin gas shares the stage with a dash of conventional dark matter. But with each adjustment, the theory loses some of its original elegance, the very quality that made it so appealing. What's left is a cautionary tale about the universe's knack for defying simple solutions. Chaplygin gas remains a fascinating what if, a reminder that sometimes the cosmos prefers complexity over unity. And while it might not be the final answer, its legacy lives on, inspiring new ideas about how dark matter and dark energy could still be two faces of the same enigmatic coin. What if gravity isn't a fundamental force at all, but more like the steam rising from a cup of coffee, a side effect of something deeper? This is the radical premise of entropic gravity, a theory that rewrites Einstein's playbook by suggesting gravity emerges from entropy, the universe's tendency toward disorder. Picture a crowded dance floor. No one's pushing or pulling, but the way dancers move and shuffle creates the illusion of forces at work. In this view, spacetime itself might be a stage where gravity isn't an actor but the choreography emerging from the chaos. The idea was pioneered by Dutch physicist Erik Verland in 2010, who proposed that gravity isn't an innate force but a statistical phenomenon, a consequence of information scrambling at the quantum level. Think of it like this: when you heat a gas, its molecules move faster, and the system's entropy increases. Verland argues that spacetime behaves similarly. Massive objects like stars or galaxies distort the information density of space, creating what we perceive as gravity. The kicker, this approach doesn't just redefine gravity, it might make dark energy obsolete. If gravity is an entropic effect, the universe's accelerating expansion could simply be nature's way of maximizing disorder, no mysterious dark energy required. The math behind entropic gravity borrows from thermodynamics and holography, suggesting that what we call gravity is actually a gradient in the universe's information content. Imagine a rubber sheet stretched tight with tiny pixels, each holding bits of data. Place a heavy object on it, and the pixels rearrange, creating a dip we interpret as gravity. But unlike Einstein's spacetime, which bends under mass, Verlan's version bends under information, a subtle but profound shift. This could explain why galaxies rotate faster than predicted without invoking dark matter. The extra force isn't hidden matter but a byproduct of entropy's invisible hand. Critics argue entropic gravity is more philosophy than physics, a clever metaphor lacking experimental proof. After all, Newton's and Einstein's theories have been tested to exquisite precision, from falling apples to gravitational waves. Yet Verlan's model makes startling predictions, like correctly estimating the rotation speeds of galaxies without dark matter, a feat traditional models struggle with unless they tweak their formulas. Supporters also point to black hole thermodynamics, where entropy and gravity intertwine so tightly that Hawking radiation practically screams for a deeper connection. The stakes are cosmic. If entropic gravity holds up, it wouldn't just eliminate dark energy, it would mean our universe runs on information, not forces. Spacetime becomes a cosmic hard drive and gravity its way of defragmenting. But until we can test this in labs or observe its fingerprints in the cosmos, the theory remains a provocative what if. Still, in a universe where 95% of everything is missing, maybe the answers aren't in the stars but in the silent hum of entropy itself, the universe's way of keeping score. Negative mass sounds like science fiction, but in the equations of physics, it's a tantalizing possibility, one that could rewrite our understanding of dark energy. Picture a particle that doesn't just lack mass but has negative mass. Instead of being pulled toward gravity like everything else in the universe, it's repelled like two magnets pushing apart. Now imagine a cosmos filled with these phantom particles, each one exerting a kind of anti-gravity, nudging galaxies away from each other faster and faster. That's the bizarre premise of negative mass matter, a theory that turns the familiar rules of physics upside down. At first glance, negative mass seems to violate common sense. If you pushed a negative mass object, wouldn't it accelerate toward you instead of away, defying Newton's laws? Surprisingly, the math checks out mostly. General relativity actually allows for negative mass solutions as long as certain conditions hold. These exotic particles wouldn't just repel normal matter, they'd also repel each other, creating a runaway effect where the more space expands, the more negative matter spreads out, driving expansion even faster. It's a feedback loop that eerily mimics the observed effects of dark energy, but with a twist: no mysterious force required, just a cosmic ingredient with inverted properties. But here's where the theory gets thorny. Negative mass raises red flags about causality, the principle that cause must precede effect. If a negative mass particle is repelled by gravity, does that mean it falls upward in a gravitational field? Would it travel backward in time? Some models sidestep these paradoxes by proposing that negative mass matter isn't entirely independent, but always exists in pairs with positive mass, canceling out the weirdest implications. Think of it like cosmic bookkeeping. For every negative mass particle pushing outward, there's a counterpart anchoring it to the usual laws, keeping the universe from unraveling. Critics argue that negative matter is less a solution and more a sleight of hand, replacing one mystery, dark energy, with another, a substance we've never detected. Yet the idea has stubbornly persisted because it offers something rare, a way to explain cosmic acceleration without inventing new physics. if negative mass exists, even in trace amounts woven through the vacuum of space, its collective push could be the engine behind the universe's expansion. The real test lies in the details. Negative mass would leave subtle fingerprints, like distortions in the way galaxies cluster or anomalies in gravitational lensing. So far, searchers have turned up empty, but the hunt isn't over. After all, if 95% of the universe is invisible, why wouldn't some of it have the wrong sign on its cosmic paycheck? Whether a dead end or a paradigm shift, negative mass challenges us to ask, in a cosmos this strange, which rules are fundamental and which are just waiting to be broken? What if the universe's missing energy isn't vanishing, just trapped in the microscopic cracks of spacetime itself? That's the bold claim of loop quantum gravity, a theory that reimagines the fabric of reality not as smooth and continuous, but as a shimmering network of tiny, interconnected loops. Think of spacetime as a finely woven tapestry, where each thread is a minuscule loop of gravitational field, knotted together at scales a billion times smaller than an atom. In this pixelated cosmos, energy isn't lost, it's woven into the very structure of existence, hiding in the gaps between the quantum stitches of gravity. Unlike string theories, vibrating strings dancing in extra dimensions, loop quantum gravity keeps things closer to home, anchored in the three-dimensional universe we know, but with a revolutionary twist. Here, spacetime isn't infinitely divisible, it's granular like sand on a beach. Try to zoom in far enough and you'd hit a smallest possible unit of space, a quantum of volume, beyond which no measurement makes sense. This granularity isn't just philosophical, it could solve dark energy's puzzle. If spacetime itself is made of discrete chunks, their interactions might naturally generate the repulsive force we call dark energy, like water pressure building between microscopic cracks in a dam. But loop quantum gravity's wildest idea isn't just about missing energy, it's about the birth of the universe. The theory offers an alternative to the Big Bang's fiery singularity, proposing instead a big bounce. Picture the universe not exploding from nothing, but rebounding like a compressed spring. In this model, our expanding cosmos was once a collapsing one, squeezed to unimaginable density until quantum gravity's granular spacetime kicked in, reversing the collapse into expansion. The energy we can't account for today, it might be leftover tension from that cosmic rebound, still echoing through the loops of spacetime like the hum of a plucked guitar string. The implications ripple outward. If spacetime is granular, then Einstein's smooth continuum is an illusion, a mirage that only holds at large scales. Up close, the universe is a seething foam of quantum connections where energy conservation could work differently. In standard physics, energy can't be created or destroyed, but in loop quantum gravity, it might leak between the quantum threads, appearing to vanish from our macroscopic view while remaining woven into spacetime's hidden architecture. Critics argue the theory is still more math than observation, a beautiful framework without experimental proof, yet it makes testable predictions like subtle tweaks to how light travels across the universe. If spacetime is granular, the highest energy cosmic rays might stumble on its microscopic bumps, leaving faint scars in their spectra. Future detectors like the Cherenkov telescope array could hunt for these fingerprints. For now, loop quantum gravity remains a thrilling what if, a reminder that the universe's greatest mysteries might not lie in distant galaxies, but in the invisible quantum knots tying reality together. And if it's right, dark energy isn't missing. It's just waiting for us to learn the language of spacetime's smallest whispers. What if the universe has a hidden twin, a perfect copy of every particle, every star, every galaxy, but completely invisible to us? This isn't science fiction, it's the startling premise of mirror matter theory. Imagine a shadow world where atoms, planets, even life might exist, but with one crucial difference. These mirror particles don't interact with light or ordinary matter. They pass right through us, unseen and unfelt, leaving only the faintest gravitational fingerprint. That's the tantalizing idea behind mirror matter, a parallel cosmos woven into our own, silently shaping the universe with its unseen weight. Here's how it could solve the dark matter puzzle. When astronomers measure the gravitational pull of galaxies, they find far more mass than visible stars and gas can account for. Mirror matter offers an elegant solution. What if that extra gravity comes from a mirror version of our own Milky Way, overlapping it like a ghostly double? Just as your reflection mimics your movements without ever touching you, mirror galaxies would perfectly trace the structure of visible ones, their collective mass explaining why real galaxies spin faster and cluster differently than they should. No exotic particles needed, just a hidden twin to everything we know, tugging on spacetime from behind the cosmic curtain. The math behind this is surprisingly straightforward. If mirror particles exist, they'd obey nearly identical physics to ordinary matter. Same forces, same laws, but with one critical exception. They'd only interact with our world through gravity. Picture two orchestras playing the same symphony in perfect unison, but separated by soundproof glass. Each follows the same score, yet neither hears the other. In this analogy, gravity isn't part of the music. It's the vibration of the stage itself, felt by both ensembles. That shared stage is space-time, the only bridge between our matter and its mirror counterpart. For decades, scientists dismissed mirror matter as untestable speculation, but recent observations have breathed new life into the idea. Take neutron stars, ultra-dense stellar corpses so heavy they warp spacetime like bowling balls on a trampoline. Some exhibit puzzling cooling rates that defy conventional physics, as if invisible particles are sapping their heat. Mirror matter could explain this. A neutron star's mirror twin, lurking unseen inside it, might subtly alter its behavior. Even more compelling are certain cosmic rays, high-energy particles from deep space, that arrive with unexpected properties, as if they've ricocheted off hidden mirror galaxies we can't see. Yet mirror matter isn't without its skeptics. If whole mirror galaxies exist, why hasn't their gravity distorted the light from distant stars in ways we can clearly spot? Why don't we see mirror planets subtly amplifying starlight as they pass in front of stars, a phenomenon called gravitational microlensing? Some theorists tweak the model, suggesting mirror matter might interact very weakly with ordinary matter, not completely, but just enough to leave subtler traces. Others propose that mirror particles are slightly heavier than their ordinary counterparts, creating asymmetries that could explain dark matter's specific distribution. The most audacious twist: mirror matter might not just be dark matter. It could be dark energy too. If the mirror universe has its own forces and particles, perhaps its version of electromagnetism or nuclear physics differs in key ways. Maybe mirror stars burn out faster, leaving behind a sea of invisible energy that permeates space. Or maybe mirror matter decays over time, releasing energy that pushes our universe apart. It's a cosmic two-for-one, one invisible world solving two of cosmology's biggest riddles. Whether mirror matter exists remains an open question, but it forces us to confront a profound possibility. The universe might not just be stranger than we imagine, it could be stranger than we can imagine, with entire layers of reality hidden in plain sight. And if we're ever to find them, we'll need to stop looking for shadows and start listening to the gravity they leave behind. Deep in the hearts of galaxies, lurking behind veils of dust and swirling stars, supermassive black holes defy comprehension, not just by crushing matter into oblivion, but possibly by shaping the very expansion of the universe. Recent studies have thrown astrophysics into a frenzy with a radical proposal. What if these cosmic monsters aren't just passive vacuum cleaners, but engines of dark energy themselves? Imagine a black hole's core not as a dead end, but as a cosmic rechargeable battery, its growth subtly injecting energy into the fabric of spacetime. The clues emerged unexpectedly. When scientists mapped the growth of supermassive black holes across cosmic time, they noticed something bizarre. Their mass correlates suspiciously well with the universe's accelerating expansion. It's as if every time one of these giants swallowed a star, the universe itself got a tiny push outward. The math hints at a mind-bending connection. Black holes might contain vacuum energy in their cores, a relic of their formation that doesn't dilute as the universe expands. Unlike ordinary matter, which thins out over time, this trapped energy could remain potent, acting like a cosmic pressure cooker that never loses steam. Here's where it gets wilder. Einstein's equations allow for a phenomenon called gravastar's hypothetical objects, where a black hole's singularity is replaced by a bubble of dark energy. Picture a cosmic matryoshka doll, outside a shell of ultra-dense matter, inside a seething pocket of repulsive energy. If even a fraction of real black holes harbor such cores, their collective influence could mimic dark energy's effects. Every galaxy center would house a tiny anti-gravity reactor, quietly counteracting the pull of ordinary matter over billions of years. But how do you test such a theory? Astronomers turn to ancient elliptical galaxies, stellar retirement homes where black holes have finished their frenzied feeding. By measuring their masses across different cosmic epochs, researchers found a puzzling consistency. These black holes appear heavier than merger models predict. It's as if they gained weight not by eating stars, but by drawing energy from the universe's expansion itself. Critics argue it might be a coincidence, or worse, a measurement error. Yet the correlation persists, glimmering like a signpost in the dark. The implications rewrite cosmic history. If black holes are dark energy's source, then the universe's fate hangs on their evolution. In the distant future, as galaxies fade and stars burn out, these gravitational behemoths might become the dominant players, their cores pumping out dark energy long after everything else has turned to dust. No big rip, no silent freeze, just a slow, inexorable push from the darkest objects in existence. Of course, the theory isn't bulletproof. Some simulations suggest black hole growth alone can't account for all of dark energy's observed effects. Others warn that we're conflating correlation with causation, but in a field where 95% of the universe remains unexplained, even controversial ideas deserve their day. Whether black holes are cosmic puppeteers or mere bystanders, one thing's clear: the answers aren't just hidden in the voids between galaxies. They might be lurking in the darkest hearts of them all. Somewhere between the particles we know and the empty void of space, there might exist something even stranger, a shadowy sector of reality where the usual rules of mass and energy break down entirely. Welcome to the bizarre world of unparticles, a theoretical concept so radical it redefines what matter even means. Unlike protons or electrons, which have definite masses and properties, unparticles are scale invariant, meaning they don't play by the quantum rulebook. Imagine a substance that behaves less like a collection of discrete objects and more like a fog, spreading seamlessly across space without fixed positions or momenta. The idea was born from a simple question: what if there's an invisible sector of physics where particles don't act like particles at all? In 2007, physicist Howard Georgi proposed that certain high-energy theories could produce these exotic unparticles, which don't fit neatly into our standard model. They're not quite matter, not quite energy, more like ghosts in the cosmic machine, flitting through the universe without leaving conventional traces. Yet their influence could be everywhere. Because unparticles don't have fixed masses, they might interact with ordinary matter in unpredictable ways, mediating unseen energy transfers that masquerade as dark energy's effects. Picture a cosmic game of telephone where the messengers aren't electrons or photons, but something far more elusive. Unparticles could carry energy across vast distances without the usual decay, slipping between galaxies like whispers through a crowd. Their scale invariance means they don't weaken with distance the way light does. a burst of unparticle energy released billions of years ago might still resonate today, subtly nudging the universe's expansion. It's as if dark energy isn't a force at all, but the footprint of these phantom intermediaries quietly redistributing reality's balance. The implications get wilder. If unparticles exist, they could form invisible structures, cosmic filaments or webs entirely distinct from the dark matter scaffolding we've searched for. These wouldn't clump like ordinary matter but stretch and fade like smoke, creating faint gravitational anomalies that telescopes might miss. Some theories even suggest unparticles could leak energy between dimensions, acting as conduits to hidden realms. Of course, the biggest hurdle is detection. Unparticles, by their nature, resist traditional observation. They wouldn't show up in particle colliders the way Higgs bosons do, and their interactions with light might be vanishingly rare. But physicists aren't giving up. Some hunt for their fingerprints in the precise orbits of neutron stars, where unexplained gravitational tugs could hint at unparticle mediation. Others analyze the cosmic microwave background for statistical anomalies, subtle temperature fluctuations that don't fit standard models. Critics dismiss unparticles as mathematical fantasy, a clever idea with no experimental grounding. But in a universe where 95% of everything is missing, perhaps it's not the theory that's outlandish, but our insistence that the answers must fit the categories we've already imagined. After all, if history teaches us anything, it's that reality rarely obeys the limits of human intuition. And if unparticles are out there, they're not just hiding the universe's missing energy, they're rewriting the rules of the game itself. The lambda-CDM model has been cosmology's gold standard for decades, a tidy framework where dark energy, represented by Einstein's cosmological constant, stays perfectly uniform across space and time. But what if that constancy is an illusion? A growing faction of scientists argues that dark energy might be a shapeshifter, its strength ebbing and flowing over cosmic epochs. This isn't just a tweak to the model, it's a full-blown rebellion against one of modern physics' bedrock assumptions, fueled by data that refuses to fit neatly into boxes. Take supernova, those brilliant stellar explosions we use as cosmic mile markers. When astronomers compared distant supernova flares from billions of years ago to their modern counterparts, something odd emerged. The older explosions suggested dark energy was weaker in the universe's youth, as if the cosmos had been expanding slower than lambda-CDM predicts. Fast forward to measurements of the cosmic microwave background, the afterglow of the Big Bang, and the story flips. The CMB's snapshot of the early universe aligns too well with constant dark energy, leaving no room for variation. It's like trying to solve a puzzle where half the pieces insist the sky is blue while the others swear it's green. This contradiction has birthed a zoo of competing theories. Some propose dark energy awakened relatively recently, lying dormant until 5 billion years ago before surging to dominance. Others imagine it oscillates like a cosmic pendulum, alternately fueling and slowing expansion in cycles. Then there's the early dark energy camp, suggesting a fleeting burst of repulsive force in the universe's first seconds could explain the CMB's smoothness while still allowing for later shift. Picture a car that starts with a gentle press on the gas, then suddenly floors the accelerator, except no one knows why or when the driver changed their mind. The stakes are cosmic. If dark energy varies, it could mean Einstein's cosmological constant is a mirage replaced by something far stranger, a dynamic field with moods or even multiple phases like water turning to ice. That wouldn't just rewrite textbooks, it could upend our predictions for the universe's fate. A constant lambda-CDM universe heads toward a lonely but predictable heat death. But a universe with fickle dark energy, it might someday collapse in a big crunch, rip itself apart, or even oscillate eternally between expansion and contraction. Yet proving this is like trying to track a shadow with a flashlight. current telescopes lack the precision to measure subtle drifts in dark energy's strength across billions of years. That's where next-generation tools like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope come in. By mapping millions of galaxies and supernova with unprecedented detail, they could catch dark energy in the act of changing its tune, or confirm it's been a steady hum all along. Whether a revolutionary insight or a dead end, the debate itself is a victory for science. It's a reminder that even our best models are provisional, and the universe has a habit of surprising those who claim to understand it. After all, if 95% of reality is missing, shouldn't we expect the remaining 5% to be full of plot twists? Neutrinos are the universe's most elusive particles, tiny, nearly massless ghosts that stream through matter as if it weren't even there. Trillions pass through your body every second, leaving no trace. But what if these cosmic phantoms have secretive, heavier cousins that could solve not one but two of cosmology's biggest puzzles? Enter sterile neutrinos, a hypothetical breed of neutrino so shy, they don't even interact with the feeble force that ties ordinary neutrinos to the rest of reality. These shadowy particles might be more than just dark matter candidates. They could be the missing link to dark energy itself. Unlike their known counterparts, sterile neutrinos wouldn't just ignore matter, they'd ignore light and even the weak nuclear force, communicating only through gravity. That makes them perfect dark matter suspects, drifting unseen through galaxies like silent anchors, their collective mass explaining why stars orbit faster than they should. But here's the twist. Some theories suggest these particles might decay over cosmic time, releasing energy that subtly accelerates the universe's expansion. It's a two-for-one deal. Sterile neutrinos start as dark matter, then morph into a dark energy-like effect as they fade away. The hunt for these invisible particles is already underway. Deep beneath the ice of Antarctica, the Ice Cube Neutrino Observatory scans for faint flashes of light caused by ordinary neutrinos colliding with atoms. But scientists are also probing the data for anomalies, unexpected energy patterns or gaps in detection that might hint at sterile neutrinos slipping through the cracks. Meanwhile, lab experiments like Fermilab's short baseline neutrino program are blasting beams of particles at detectors, searching for oscillations, tiny quantum jumps that could betray sterile neutrinos' presence. Even the cosmic microwave background might hold clues, with certain temperature fluctuations fitting sterile neutrino models better than traditional dark matter theories. But the story isn't without skeptics. If sterile neutrinos are out there, why haven't we caught one yet? Some argue their hypothetical properties, like their mass and decay rate, require such fine-tuning that the theory feels more like wishful thinking than hard science. Others point to conflicting data. Certain astrophysical observations, like the way dwarf galaxies cluster, don't quite match sterile neutrino predictions. Yet the allure persists. If sterile neutrinos exist, they'd bridge the gap between particle physics and cosmology, offering a unified explanation for the universe's two greatest enigmas. And while the evidence is still thin, the search itself is reshaping how we think about the invisible cosmos. After all, in a universe where 95% of everything is hidden, the answers might not lie in what we can see, but in the whispers of particles we've only just begun to imagine. What if the smooth, continuous spacetime we take for granted is just an illusion, an emergent property of something far stranger happening at the quantum level? This is the mind-bending premise of emergent spacetime, a theory that suggests reality isn't built on a fixed stage of space and time, but stitched together by an invisible web of quantum entanglement. Picture the universe not as a static arena where particles interact, but as a dynamic tapestry woven from countless threads of information, with every connection between particles secretly defining the very fabric of distance and duration. At the heart of this idea is entanglement, that eerie quantum phenomenon where particles become so deeply linked that the state of one instantly influences the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, but what if this spookiness isn't just a quirk? It's the foundation of reality. In emerging spacetime models, every entangled connection acts like a tiny stitch in the cosmic quilt, with the overall pattern of these stitches giving rise to what we perceive as the geometry of space and the flow of time. It's as if spacetime itself is a hologram projected from a deeper, more fundamental layer of quantum information. Now, here's where dark energy enters the picture. If spacetime emerges from entanglement, then its properties, like the rate of cosmic expansion, might not be governed by Einstein's equations alone, but by the thermodynamics of information flow. Think of the universe as a vast computer, constantly processing and rearranging quantum connections. As it expands, new space isn't just empty vacancy. It's a dynamic medium where entanglement patterns must continuously update, like pixels on a screen refreshing to display a larger image. This process isn't free, it requires energy, and some theorists argue that dark energy might be the thermodynamic cost of maintaining cosmic coherence, a kind of entanglement tax paid by the universe as it grows. The implications are staggering. In this view, dark energy isn't some exotic force or particle, but a side effect of the universe's need to stay logically consistent. Just as a steam engine loses heat to friction, spacetime might leak energy as it entangles new regions, driving the accelerated expansion we observe. This could explain why dark energy's density appears so uniform. It's not a substance filling space, but a feature of how space itself emerges from the quantum underlayer. Critics, of course, raise eyebrows. If spacetime is emergent, why does it look so smooth and continuous on large scales? And how do you reconcile this with general relativity's flawless predictions about black holes and gravitational waves? Supporters counter that emergent spacetime might only reveal its quantum stitching at extreme scales, near the Big Bang or inside black holes, while appearing seamless in our everyday cosmic neighborhood. Some even suggest that gravitational waves could carry faint imprints of this underlying structure, like ripples betraying the texture of a pond's surface. The search for evidence is pushing the limits of modern physics. Experiments like the holometer at Fermilab have hunted for space-time pixelation at the smallest conceivable scales, while theorists explore how emergent models might alter our understanding of black hole entropy or the cosmic microwave background. It's a long shot, but if they're right, the universe's greatest mystery, dark energy, might not be missing at all. It could be hiding in plain sight, woven into the very code of reality itself, waiting for us to decipher the language of quantum threads. Whether a revolutionary breakthrough or a beautiful dead end, emergent spacetime forces us to confront a humbling possibility. The stage we've always assumed was fundamental might just be the opening act of a far deeper cosmic drama. And if that's true, the answers we seek aren't in the voids between galaxies, but in the invisible quantum bonds holding them together. Imagine a universe where dark matter isn't made of heavy, sluggish particles, but of waves rippling through space like an invisible ocean. This is the world of axions, hypothetical particles so light they barely qualify as matter at all. Born from theories designed to solve a mystery in particle physics, axions were originally proposed to explain why the strong nuclear force behaves so symmetrically. But today, they've taken on a far grander role, leading candidates for dark matter with a twist. If they exist, these ghostly particles could be so light that their quantum wave nature dominates on cosmic scales, creating interference patterns vast enough to reshape the fabric of spacetime itself. Unlike traditional dark matter models that rely on hulking WIMP or sterile neutrinos, ultra-light axions would be featherweights billions of times less massive than electrons. Their behavior wouldn't resemble discrete particles at all, but sprawling quantum waves oscillating in sync across the universe. Picture a cosmic crowd doing the wave in a stadium, except the stadium is the Milky Way, and every spectator is an axion, their collective motion generating subtle gravitational undulations. On galactic scales, these waves could clump just enough to explain the extra gravity binding stars together, while their interference peaks and troughs might mimic the repulsive effects we attribute to dark energy. The math behind this is as elegant as it is speculative. Axion waves would oscillate at frequencies set by their minuscule mass, some vibrating once every few years, others over millennia. Over cosmic time, these oscillations could average out to a near-constant background energy, subtly pushing space apart. It's like dropping pebbles into a pond. Individually, each ripple fades, but if you throw in enough pebbles at just the right intervals, the water's surface starts to rise uniformly. In this analogy, dark energy isn't a mysterious force, it's the emergent effect of countless axion waves harmonizing across billions of light years. Critics point out the challenges. If axions are this light, why haven't we detected their oscillations in lab experiments? Why don't their wave-like properties disrupt the neat formation of galaxies we observe? Supporters counter that ultra-light axions would be fiendishly difficult to spot, their signals buried in quantum noise, while their interference patterns might be too vast for current telescopes to resolve. Some even suggest that axion waves could explain anomalies in the cosmic microwave background, those faint temperature variations that serve as a baby picture of the universe. The hunt for axions is already underway, with experiments like ADMX using ultra-sensitive microwave cavities to listen for their faint whispers. Others scour pulsars, fast-spinning neutron stars, for rhythmic glitches that might betray axions' presence. And if these searches pay off, the payoff would be staggering, not just an answer to dark matter, but a radical new lens through which to view dark energy, not as a force, but as the universe's quietest symphony, played on strings we're only beginning to hear. Whether axions are the key to cosmology's greatest mysteries or just another beautiful dead end, their story embodies science at its most daring. In a field where the answers lie in the unseen, sometimes the boldest ideas aren't just worth considering, they're the only ones left to try. Why is there something instead of nothing? This isn't just philosophy, it's one of physics' greatest unsolved puzzles. Our universe runs on a glaring accounting error. For every billion particles of matter, there was once an equal amount of antimatter. They should have annihilated each other completely in the Big Bang's aftermath, leaving behind only pure energy. Yet here we are in a cosmos made almost entirely of matter. That missing antimatter might hold the key to another cosmic discrepancy, the universe's vanishing energy. Enter CPT symmetry, the sacred rule that says every particle interaction should look identical if you simultaneously flip charge c, parity p, and time t. It's physics' ultimate balancing act, but our matter-dominated universe suggests CPT might occasionally stumble, creating tiny cracks where antimatter vanishes and energy slips through. Picture a cosmic seesaw. Every time an antimatter particle winks out of existence, perhaps its energy doesn't just disappear. It gets funneled into the vacuum of space itself, becoming part of dark energy's mysterious reservoir. Certain grand unified theories take this further. In these models, the same processes that gave matter its 1 in a billion advantage could have also tweaked the vacuum's energy density. Imagine early universe conditions so extreme that particle collisions didn't just produce matter, they warped spacetime's very structure. Some of that distortion might have frozen into the fabric of reality, lingering today as dark energies push. It's as if the universe's original matter-antimatter fights left scars in spacetime, not just an imbalance of stuff, but an imbalance of energy waiting to be accounted for. The math gets dizzying here. Some CPT-violating models suggest antimatter's disappearance didn't just leave behind protons and electrons, it generated a subtle pressure in the quantum vacuum. Think of blowing up a balloon with tiny holes. The air escaping isn't gone, it's just redistributed. Similarly, every annihilated antimatter particle might have leaked energy into the vacuum's background hum. Over billions of years, these micro-contributions could add up to the repulsive force we call dark energy. Critics argue this relies on too many hypothetical dominoes falling perfectly. Yet tantalizing clues emerge from particle colliders. When scientists at CERN trap anti-hydrogen atoms, they've spotted minuscule behavioral quirks, differences in how antimatter falls under gravity or absorbs light. These anomalies, if confirmed, could hint at CPT violations big enough to fuel both our matter-filled universe and its accelerating expansion. The ultimate test may lie in the cosmic microwave background. If antimatter's disappearance truly shaped dark energy, its fingerprints might linger in that primordial glow's polarization patterns. Future observatories like the Simon's Array could hunt for these whispers from the universe's first seconds, a time when antimatter wasn't just a lab curiosity, but half of everything. Until then, this theory remains a beautiful gamble that two of cosmology's greatest mysteries might share a single, spectacular solution. Cosmic strings sound like something from science fiction, threads of pure energy thinner than an atom but stretching across the entire universe, carrying more mass than a mountain range packed into every inch. These hypothetical relics from the Big Bang aren't your average celestial objects. They're topological defects, kinks in the fabric of spacetime itself, formed when the young universe underwent violent phase transitions like cracks freezing into ice. And if they exist, their gravitational footprints could be rewriting the rules of cosmic expansion right under our noses. Picture spacetime as a bedsheet pulled taut. Now twist one section so fiercely that it kinks, creating a flaw that can't be smoothed out. That's a cosmic string, a flaw so stable it might have survived for 13.8 billion years. Unlike black holes, which warp space into pits, strings would slice through it like razor wires, creating lensing effects so sharp they'd bend light into perfect double images without any blurring. Galaxies behind a string wouldn't just appear distorted, they'd show up twice, mirrored along the string's length like reflections in a funhouse mirror. But here's where dark energy enters the story. Cosmic strings don't just sit there, they vibrate, whip, and occasionally snap, releasing bursts of gravitational waves that ripple through the cosmos. Some theories suggest these vibrations could mimic dark energy's repulsive effects, not by pushing space apart but by altering how we perceive its expansion. Imagine measuring a rubber band stretch while invisible fingers pluck it. You might mistake the tension for some mysterious force. Similarly, strings' gravitational ping could skew our measurements of the Hubble constant, making the universe seem like it's accelerating when it's really just ringing. Then there's dark matter. Strings are so dense that even a single loop weighing as much as a star would be nearly invisible, detectable only through its gravity. If the early universe spawned a network of these filaments, they could weave through galaxies like unseen scaffolding, their collective pull masquerading as dark matter's grip. The math gets tantalizing here. Certain string configurations could explain why galaxies rotate faster at their edges without needing WIMP or axions. It's as if dark matter was never a particle at all, just the ghostly tug of spacetime's ancient scars. Of course, finding proof is like hunting for spider silk in a hurricane. Strings are so thin they'd rarely pass between Earth and distant stars, making their lensing effects incredibly rare. Yet astronomers have scoured quasar surveys for those telltale double images, and gravitational wave detectors like LIGO listen for the faint ping of a snapping string. So far, silence, but absence of evidence isn't evidence of absence. Cosmic strings might be so sparse that we'd need to survey millions of galaxies to spot one. Or perhaps they've decayed over eons, leaving only faint gravitational echoes. Either way, they remind us that the universe's missing energy might not be hiding in particles or fields, but in the twisted geometry of spacetime itself, waiting for us to trace its frayed edges. Gravity's grip seems instantaneous. Reach out, and Earth pulls you down without delay. But according to Einstein, its influence travels at light speed, just like everything else in the universe. What if that's not entirely true? Non-local gravity theories turn this assumption upside down, proposing that gravitational effects might transcend the usual speed limits, rippling across the cosmos in ways that could rewrite dark energy's role entirely. Imagine tossing a pebble into a pond. In our current understanding, the ripples spread outward at a fixed speed, just like gravity's influence. But non-local gravity suggests the pond itself has a memory, where past ripples subtly shape future ones, creating effects that appear to leap across distances. Apply this to cosmology, and suddenly, the universe's expansion might not need dark energy at all. Instead, the gravitational pull of distant galaxies could reach us with a delay, their ancient influence still acting on us today in a way that mimics an accelerating cosmos. It's as if the universe is haunted by its own past, with ghostly gravitational echoes pushing galaxies apart. The math behind this is dizzying. Equations that normally demand dark energy's repulsive force can be tweaked to include non-local terms corrections that account for gravity's lingering effects over billions of years. Picture a cosmic game of telephone where the messages aren't just delayed, but layered, with each epoch's gravitational whispers stacking up to shape how space stretches today. Some models even suggest this could explain why the universe's expansion rate seems to fluctuate across different measurements, like Hubble tension, an artifact of gravity's non-local echoes from different cosmic eras. Critics argue this dance is dangerously close to action at a distance, a concept physics abandoned centuries ago. Yet supporters point to quantum entanglement, where particles instantly influence each other across vast distances, as proof that non-locality isn't just possible, it's fundamental. Could gravity, at some level, play by similar rules? The challenge is testing it. If non-local gravity is real, its fingerprints might hide in subtle anomalies, like galaxies whose motions defy predictions or gravitational waves arriving with unexpected timing. Future observatories like the Laser Interferometer Space Antenna could hunt for these discrepancies. What's fascinating is how this flips the script. Dark energy becomes less about an unknown force and more about a cosmic lag, a side effect of gravity's long memory. The universe isn't speeding up, we're just feeling the aftershocks of its ancient rhythms. Whether a revolutionary insight or a mathematical mirage, non-local gravity forces us to ask, are we missing something fundamental about how the cosmos remembers itself? At the smallest scales imaginable, spacetime isn't smooth and serene. It's a chaotic, boiling froth of quantum activity. This is the realm of quantum foam, a concept so turbulent it makes stormy oceans look like glass. Picture the vacuum of space not as empty, but as a seething ocean where particles and antiparticles constantly blink in and out of existence, creating a froth of fleeting energy fluctuations. These aren't just mathematical abstractions, they're real phenomena proven by effects like the Casimir force, where two metal plates in a vacuum are subtly pushed together by the sheer pressure of virtual particles popping into being around them. Now here's the kicker. If you could add up all this frenetic quantum activity, every particle pair appearing and vanishing in Planck-sized bubbles of spacetime, the total energy should be colossal. We're talking about a number so large it would make the observable universe's mass look like a rounding error. Yet when we measure dark energy's actual effect on cosmic expansion, it's absurdly weak by comparison, like comparing the roar of a supernova to the rustle of a single leaf. This staggering mismatch is known as the cosmological constant problem, and it's one of the most glaring unsolved puzzles in physics. So where does all that quantum foam energy go? One possibility is cancellation. Maybe the froth's positive and negative fluctuations mostly balance out, leaving behind only a faint residual energy we perceive as dark energy. Think of it like a frenzied stock market where wild price swings average out to a modest trend over time. But even this explanation feels shaky. The imbalance we observe is still 1 part in 10 to the power of 120, a number so unimaginably precise it reeks of fine-tuning. Or perhaps we're missing something deeper. Some theorists argue that quantum foam doesn't just contain energy, it fundamentally alters how gravity works at microscopic scales. In this view, spacetime's foamy texture might act like a cosmic filter, smearing out extreme energies before they can influence the larger universe. Imagine trying to push water through a sponge. The sponge's structure determines how much gets through, no matter how hard you squeeze. Similarly, quantum foam's turbulence could naturally suppress vacuum energy's full strength, leaving only the whisper we call dark energy. The challenge. Testing these ideas requires probing spacetime at scales a trillion times smaller than an atom, far beyond any microscope's reach. Yet indirect clues might lurk in high-energy astrophysics. If quantum foam leaves even faint imprints on light traveling billions of light-years, telescopes like the upcoming Cherenkov telescope array could spot subtle distortions in gamma-ray bursts. Others hunt for anomalies in atomic clocks, where ultra-precise timekeeping might reveal spacetime's frothy graininess. Whether a fundamental feature of reality or a mathematical mirage, quantum foam forces us to confront a humbling truth: the vacuum of space is anything but empty. It's a writhing, dynamic medium, and somewhere in its chaos might lie the secret to why the universe refuses to sit still. What if dark matter and dark energy aren't separate entities at all, but two faces of the same enigmatic substance, a cosmic chameleon that shifts its behavior based on the universe's ever-changing conditions? Enter dark fluid, a radical theory that seeks to unify the universe's two greatest mysteries into a single, exotic medium. Picture a material that acts like invisible matter in the dense heart of galaxies, clumping under gravity to sculpt their rotation, but transforms into a repulsive force in the vast emptiness between them, pushing the cosmos apart. It's as if the universe's missing ingredients were never distinct, just different phases of one shadowy, shape-shifting soup. The inspiration for this idea comes from an unexpected place: chaplogen gas, that peculiar hypothetical substance we explored earlier. Like dark fluid, chaplogen gas can mimic dark matter's gravitational grip in high-density regions while behaving like dark energy as it thins out. But dark fluid takes this concept further, proposing a more dynamic and adaptable substance, one whose properties aren't just tied to density, but to the universe's expansion rate, temperature, or even unseen quantum fields. Imagine a cosmic thermostat, where the same fluid cools into dark matter's sticky grip or heats into dark energy's repulsive push depending on the environment. Observational clues both tantalize and frustrate. On one hand, dark fluid neatly sidesteps the awkwardness of needing two unrelated dark components dominating the cosmos. It could explain why dark energy seemed to turn on around 5 billion years ago, not because of some cosmic switch, but because the fluid's internal pressure finally overcame gravity's pull as the universe diluted. On the other hand, precise measurements of the cosmic microwave background throw curveballs. The way matter clumped in the early universe suggests dark matter's influence was too consistent, too particle-like, for dark fluid's flexible nature to fully explain. It's like trying to fit a squishy, morphing puzzle piece into a rigid slot. Theorists aren't giving up. Modified dark fluid models propose hybrid behaviors. Perhaps the fluid interacts with itself through hidden forces or segregates into distinct phases under extreme conditions. Others suggest dark fluid might leave faint imprints in gravitational wave signals, subtle ripples that betray its presence. Future telescopes, like the European Space Agency's Euclid mission, could scan the cosmos for these fingerprints, hunting for anomalies in how galaxies cluster or how light bends around cosmic voids. Critics argue dark fluid is a clever sleight of hand, a way to dodge the hard work of explaining two unsolved problems by smashing them into one, yet its elegance is undeniable. In a universe that constantly reinvents itself, why shouldn't its darkest secrets do the same? Whether a unifying breakthrough or a beautiful dead end, dark fluid forces us to ask, are we overcomplicating the cosmos by inventing separate mysteries when the truth might be fluid all along? The holographic principle shook physics to its core by suggesting reality might be a projection, but what if it also holds the key to dark energy? Enter holographic dark energy, a theory that ties the universe's accelerating expansion not to some mysterious substance, but to the fundamental limits of information itself. Imagine the cosmos as a giant sphere, its surface area dictating how much energy can exist within it, like a cosmic data cap written into the fabric of space. The more the universe expands, the larger its horizon becomes, and with it, the energy density required to fill that growing surface. This idea stems from entropy bounds, rules that limit how much information, and by extension, energy can be packed into a region of space. In the late 1990s, physicist Raphael Bousso showed that the maximum entropy in any volume isn't proportional to its size, but to the area of its boundary. It's as if the universe stores its secrets on a two-dimensional shell, with the interior just playing out the projection. Apply this to dark energy, and suddenly its eerie uniformity makes sense. It's not a fluid filling space, but a property of spacetime's informational edges, like the pixels on a screen determining the brightness of the image. The math here is both elegant and radical. Holographic dark energy's density depends on the inverse square of the Hubble horizon, the distance beyond which light hasn't had time to reach us since the Big Bang. As the universe expands, this horizon grows, and the energy density evolves in lockstep. Contrast this with the standard lambda-CDM model, where dark energy remains stubbornly constant, a fixed background noise. Holographic dark energy, by contrast, is dynamic, its strength subtly changing as the cosmic horizon stretches. Observational clues tease us with possible support. Measurements of the universe's expansion rate fit holographic models slightly better than lambda-CDM at certain redshifts, hinting that dark energy might not be a cosmological constant after all. Even more compelling are entropy calculations. Black holes, the universe's ultimate information scramblers, obey holographic rules so precisely that it's hard to ignore the parallel. If spacetime itself is a hologram, why wouldn't its energy play by the same rules, yet tensions remain? The holographic model predicts a specific relationship between dark energy and matter densities that doesn't quite match current galaxy clustering data. And while it elegantly sidesteps the cosmological constant problem, that infamous 1 in 10 to the 120 mismatch, it introduces its own puzzles, like why the universe's informational bounds would manifest as repulsive gravity. Critics argue holographic dark energy is a beautiful abstraction in search of concrete evidence, but supporters counter that it's the only framework where dark energy isn't an arbitrary add-on but a natural consequence of spacetime's deepest structure. Future galaxy surveys like Daisy and Euclid could tip the scales, hunting for deviations from lambda-CDM's predictions that might reveal the universe's holographic heartbeat. Whether a revolution or a mirage, this idea forces us to confront a staggering possibility. The energy we've been chasing might not be in the universe at all, but etched onto its edges, a cosmic reminder that sometimes the answers aren't hidden in the depths but written on the walls. Gravity seems like the universe's most reliable force. Drop an apple and it falls every time. But what if its pull isn't as constant as we think? Imagine a secret layer of reality where gravity weakens in the vast, empty stretches between galaxies, its strength flickering like a candle in the wind. This is the essence of gravity screening, a theory that suggests dark energy might not be a mysterious substance at all, just gravity itself wearing a cosmic disguise. At the heart of this idea are chameleon fields, hypothetical energy fields that change their behavior based on the environment. Picture a lizard blending into its surroundings. In dense regions like galaxy clusters, these fields would hide, matching ordinary gravity's pull to avoid detection. But in the void, those desolate cosmic deserts where matter is scarce, they'd emerge, weakening gravity's grip and creating the illusion of a repulsive force pushing space apart. It's as if the universe has a gravitational dimmer switch, subtly turning down the lights where no one's looking. The math behind this is both elegant and slippery. Chameleon fields couple to matter in a way that makes them ultra-sensitive to density. Near a massive galaxy, the field's effects would be squashed, rendering it virtually invisible. But in the vacuum of intergalactic space, the field would stretch out, its energy unfurling like a sail catching the wind. From our perspective, this would look identical to dark energy, distant galaxies receding faster than local gravity should allow, without needing any exotic particles or extra dimensions. Just gravity playing hide and seek with itself. This isn't pure speculation. Modified gravity theories like FR gravity, where gravity's strength depends on the curvature of spacetime, already hint at similar effects. Some even predict chameleon fields should leave faint fingerprints in the way dwarf galaxies orbit their larger cousins or how light bends around cosmic voids. Experiments like the European Space Agency's microscope mission have hunted for these anomalies, measuring free-falling test masses with exquisite precision to spot gravity's slightest deviations. So far, no chameleons, but the search is far from over, yet challenges loom. If gravity weakens in voids, why don't we see more dramatic distortions in the cosmic web structure? Why does dark energy's apparent strength align so neatly with the vacuum energy predicted by quantum theory? Critics argue chameleon fields feel like a patchwork fix, a way to avoid dark energy's mysteries by tweaking gravity until it fits. But supporters counter that science has rewritten gravity before. Einstein overturned Newton when he showed gravity bends spacetime. Perhaps we're on the brink of another revolution, where gravity's rulebook gets a new chapter written in invisible ink. Whether a breakthrough or a blind alley, gravity screening forces us to confront a humbling truth. The force we thought we knew might be stranger than we imagined. And in a universe where 95% of everything is missing, sometimes the boldest answers aren't about what's there but what's hiding in plain sight. Black holes aren't just cosmic vacuum cleaners, they're information shredders. According to quantum mechanics, information can never truly be destroyed, yet black holes seem to violate this sacred rule. When matter vanishes beyond the event horizon, it takes all its quantum secrets with it, leaving no trace in our universe. Or does it? A bold new theory suggests that black holes don't erase information after all. Instead, they might be quietly transforming it into something far stranger, the universe's missing dark energy. Picture a black hole slowly evaporating through Hawking radiation, that faint glow of particles leaking away over eons. Traditionally, physicists assumed this radiation was thermal noise, random, featureless, carrying no data about what fell in. But revised models now hint that Hawking radiation could be subtly encoded with the lost information of swallowed stars and planets. The catch: preserving this data requires energy, and that energy has to come from somewhere. Some theorists argue it's siphoned from spacetime itself, creating a kind of quantum debt, an imbalance that manifests as dark energy's repulsive push. This idea turns the infamous black hole firewall debate on its head. The firewall paradox arises when you try to reconcile quantum mechanics with general relativity at the event horizon, leading to a brutal contradiction. Either information is lost breaking quantum rules, or an inferno of high-energy particles lurks just outside the horizon, breaking relativity. But if escaping information fuels dark energy, it could resolve the paradox by softening the firewall's fury. Imagine the event horizon not as a destructive boundary, but as a cosmic transformer converting mangled quantum data into the energy stretching the universe apart. The math behind this is speculative but tantalizing. Calculations suggest that the energy required to preserve information during Hawking radiation aligns suspiciously well with the observed density of dark energy. It's as if every bit of data recovered from a black hole's grasp leaves an indelible mark on the vacuum of space, like ripples spreading through a pond. Over billions of years, these micro-contributions from countless evaporating black holes could accumulate into the repulsive force we're desperately trying to explain. Critics argue this stretches plausibility. Why would information preservation affect cosmic expansion? And how does this square with the fact that dark energy's effects appear uniform, while black holes are scattered unevenly across the cosmos? Supporters counter that the universe's holographic nature might smooth out these irregularities, distributing the energy like a quantum averaging effect. Others suggest supermassive black holes at galaxy centers act as anchors, their collective information loss emissions weaving into a cohesive dark energy field. The stakes are cosmic. If true, this would mean dark energy isn't some external force, it's the universe's way of balancing its quantum books. Every dying black hole would be a silent architect of cosmic acceleration, its vanishing act fueling the expansion of spacetime itself. Future gravitational wave observatories could test this by hunting for anomalies in Hawking radiation's faint signals, or by probing the quantum fuzz around event horizons for signs of energy leakage. Whether a breakthrough or a dead end, this theory forces us to confront a profound irony. The darkest objects in existence might hold the key to the universe's brightest mystery. And if we're right, the energy we've been chasing isn't lost at all. It's just been waiting, encoded in the silent screams of black holes for us to finally listen. What if our entire universe is just one bubble in an endless cosmic foam? A single pocket of spacetime adrift in an infinite multiverse where new universes constantly sprout, collide, and stretch into existence. This is the mind-bending premise of eternal inflation, a theory that doesn't just reshape our cosmic origins, it might explain why our universe's energy ledger doesn't add up. Imagine a vast, hyperactive sea where space itself is constantly expanding at speeds beyond light's reach. In this frenzied ocean, quantum fluctuations occasionally trigger violent phase transitions like pockets of boiling water suddenly freezing into ice. Each of these transitions births a new universe, complete with its own laws of physics, while the surrounding space continues inflating endlessly, our observable cosmos. Just one tiny bubble in this infinite froth, its boundaries forever receding as the greater multiverse races onward. Now, here's where the missing energy comes in. These universes aren't isolated. Their gravitational fields can subtly interact across the cosmic foam, like ripples passing between bubbles on the surface of a pond. If a neighboring universe tugs on ours just slightly, its gravity could leak into our spacetime, manifesting as an extra nudge in the equations, a discrepancy we've labeled dark energy. It's not that energy is vanishing. We might simply be feeling the faint tremors of other realities brushing against our own. The math behind this is as elegant as it is speculative. Inflationary models suggest that during the Big Bang, our universe underwent a period of exponential expansion driven by a repulsive energy field. When that field decayed, it released the energy that became matter and radiation, but most of the multiverse kept right on inflating. In this view, dark energy could be the residue of that primordial inflation, diluted but never entirely gone, like the lingering warmth of a dying ember. Supporters point to eerie symmetries. The observed value of dark energy aligns suspiciously well with theoretical predictions of how much energy might seep between bubble universes. Even stranger, cosmic microwave background maps show odd anomalies, cold spots, and asymmetries that some interpret as bruises from long ago collisions with other universes. It's as if the cosmos bears scars from its multiversal neighbors, Yet eternal inflation isn't without its skeptics. If other universes are constantly tugging on ours, why don't we see more dramatic distortions in galaxy clustering or light from the early universe? And how do you test a theory where most of reality exists permanently beyond our horizon? Detractors argue it's less science and more metaphysics, a dazzling idea forever out of reach. But the theory's defenders aren't backing down. Some propose that advanced gravitational wave detectors could one day catch echoes of ancient bubble collisions like sonar pings from distant shores. Others suggest that subtle patterns in the distribution of quasars might betray the multiverse's texture. For now, these remain speculative whispers, yet in a universe where 95% of everything is unaccounted for, perhaps the boldest ideas are the only ones worth chasing. Whether a cosmic epiphany or a beautiful dead end, eternal inflation forces us to confront a staggering possibility. The answers we seek might not lie within our universe at all, but in the infinite beyond, where countless other realities stretch into the dark, each one rewriting the rules of existence in ways we're only beginning to imagine. What if the universe's missing energy isn't lost, just allocated to running the cosmic simulation we call reality? The simulation hypothesis, once relegated to sci-fi and philosophy debates, has gained surprising traction among some physicists as a tongue-in-cheek explanation for dark energy's ghostly presence. Picture our universe as an unimaginably advanced computer program, where dark energy represents the processing power needed to render distant galaxies while optimizing frame rates in our local cosmic neighborhood. This wild idea stems from a simple observation. The universe behaves suspiciously like a finely tuned virtual world. Fundamental constants, the speed of light, gravitational strength, even the charge of an electron, appear perfectly calibrated to allow complexity and life. Tweak them slightly and stars, planets, and atoms would never form. To simulation theorists, this isn't luck, it's evidence of intentional programming. And just as video games simplify graphics for distant objects to save computing resources, our universe's accelerating expansion could be a clever optimization, dark energy, as the cosmic equivalent of lowering the render resolution beyond a certain radius to prevent system crashes. Even heavyweight physicists engage with the premise. Neil deGrasse Tyson has quipped there's a 50% chance we're living in a simulation, while Elon Musk famously declared the odds 1,000,000,000 to 1 against base reality. But MIT's Max Tegmark takes it further, suggesting that if our descendants ever create ancestor simulations, the statistical likelihood we're in the original universe dwindles to near zero. The logic is unsettling. With enough advanced civilizations running cosmic-scale simulations, simulated beings like us would vastly outnumber real ones, making authenticity statistically improbable. Of course, most scientists treat this as playful speculation rather than rigorous theory. For one, there's no testable mechanism. How would you distinguish a real universe from a simulated one when all measurements are part of the code? Critics also point out that simulating every quantum particle in a universe would require unfathomable energy, making the idea self-defeating. Why would hyper-advanced beings waste resources simulating cosmic voids or dinosaur bones when they could just simulate conscious experiences directly? Yet the hypothesis refuses to die, fueled by eerie quantum behaviors that feel oddly computational. Take the observer effect, where particles behave differently when measured, like a game engine only rendering graphics when players are looking. Or entanglements, instant correlations across space, which some compare to optimized data streaming between servers. Even dark energy's uniformity, its equal distribution everywhere, mirrors how a simulation might apply global physics rules consistently to save memory. The real value of this idea isn't in its plausibility, but in how it reframes our cosmic questions. If we entertain simulation theory, dark energy becomes less a physics problem and more a software design choice, an intentional constraint placed by the programmers. Maybe the missing energy isn't missing at all. It's the electricity bill for running our reality. And that might be the ultimate cosmic joke. The reason we can't find 95% of the universe is because we're not supposed to. The debug console is off limits. While few researchers bet careers on this fringe notion, its persistence highlights how desperate we are to explain the unexplainable. When equations fail and observations baffle, even outlandish ideas deserve a moment in the spotlight, if only to remind us that the universe's greatest mysteries might not just defy our laws of physics, but our very definition of reality itself. From vanishing antimatter to quantum foam, from holographic projections to cosmic strings, the hunt for the universe's missing energy has taken us down some of the wildest rabbit holes in science. What's astonishing isn't just the sheer diversity of theories, but the fact that any of them could be true. That's the beauty of cosmology. It's a field where even the most outlandish ideas get a seat at the table, as long as the math holds up. For every physicist convinced dark energy is Einstein's cosmological constant, another swears it's phantom energy doomed to rip reality apart, while a third argues we've had gravity wrong all along. And that's not chaos, it's how science works. Every wrong turn, every failed experiment, every discarded hypothesis is a step closer to the truth. So which theory grabs you? The elegant simplicity of supersymmetry's hidden particles, the haunting poetry of holograms encoding reality, or maybe the audacious idea that black holes are quietly fueling cosmic expansion with their dying breaths? There are no wrong answers, only mysteries waiting for their moment. Because here's the thing, every breakthrough in history started as a what if scribbled on a napkin or whispered in a lab. The next big leap might already be taking shape in some grad student's notebook, or in data we've yet to decode from a telescope halfway around the world. The universe isn't just stranger than we imagine, it's stranger than we can imagine, and that's why we keep looking, probing, questioning, so stay curious. Maybe you'll spot the clue everyone else missed, and if you love this dive into the cosmos's greatest enigma, hit like, subscribe, and ring that bell, because the universe has plenty more secrets to share, and we're just getting